Start recording. Before I continue, I wanted to give you one image of something I wanted to show you. I have dared to do this. I have uploaded all the lecture videos to YouTube. I don't know whether this makes sense or not, but I don't care. Um, I just wanted to try it out with all the errors, all the S's and U's, and all the corrections and help from Mr. Botta. You are not you, but your results are in slide and uploaded to YouTube. So if you are interested in, I just copy the link to the chat. One moment. So here we are. You don't have to, but if you are just curious, just click on it. So that's all. Now let's continue with this screen. Okay, before I continue my monologue, do you have questions about the topics we have talked about 1 week ago? Not yet? Just interrupt me, as all. The time you can do. Don't hesitate. I switch. Is my video, the additional video with the trees in the background, does it disturb something? Can I keep it running? Okay, so I can see me then in front of mine, whether I'm in front of the green screen or something is, yeah, something is left. I have forgotten to switch on the light. You see this? This makes this corner more bright, and I you see this black noise in the corner of the slide here. Do you see this blur? If I place this light there, this noise is gone. €5. Okay. We have had the topic in the last lecture about carrier motion. I want to wrap up where we are from the beginning. So we have silicon, then we have silicon crystal, putting it together. Then we have stuff which doesn't conduct at the first glance, but it does conduct because due to the temperature and the temperature's behavior is taken into account through Fermi-Dirac statistics and reduced in the complexity by Boltzmann statistics. We have mobile carriers because some of the covalent bonds are cracked and we generate electrons and holes. And so we have them as as the intrinsic carrier concentration. We dope, we put phosphorus into the crystal. The phosphorus has 1 electron more than required for the 4 covalent bonds in the diamond crystal lattice. And this 5th electron is quite below the conduction band H, so you need a limited energy amount of energy in terms of temperature to release the 5th electron, or vice versa. If you put boron into the crystal, you have 3 valence electrons, you need 4. The 4th is catched up from the valence band. And now we have bound to the lattice charges, space charges, and mobile carriers. In the N-type, you have phosphorus, you have electrons. The majority carriers are electrons. The P-type is doped with boron, and the majority carriers are holes. So we have these carriers, and we can push them by electric field. Then we have the drift current. The drift velocity is a function of the electrical field, and we have learned that you can increase the electrical field, thereby you can increase the drift velocity, but to a certain point, then the velocity saturates. The saturation is caused by the change in the effective mass. You can read in the AK diagram. So the saturation takes place. So we have two areas, constant mobility and constant velocity. So this we have at the moment. And on top of this, we have the thermal motion, but without net direction of the electrons or the carrier. So the temperature gives you an arbitrary movement in 3 dimensions. But at the next step, we will learn how this thermal motion will result in a net diffusion, net movement. For this, we don't only need temperature, we need a second thing, namely concentration gradient, or a difference in the concentration on different locations in the lattice. Take a look here. This is a separator. We think about it as a separator. So we have a moment in time where the area 2 has random dots. Area 1 has also random dots. These particles are randomly placed. Do you think? What do you think? What you should do to place something randomly? Is this random? Here we have a bunch of dots, and here we have a cavity. Here we have a large cavity. Is this random? What do you think? Seems to. I was surprised at the very first glance on this picture. I wanted to make a random dot, and I started to make this. And then I got tired. And then I have taken Excel and made a matrix of random figures. Then I plotted this matrix of random figures two-dimensionally. Then I have taken a look at the result and said, hey, what? That's not random. Then I said, okay, random means that you can have some areas with higher density or some areas with lower density. So the mean density is random. So this is really the random function of Excel. So I reduced the number of points for the second graph I have generated with this matrix. Now I want to show you using this graph how diffusion works. You know that if you have an area with a higher concentration of particles and a second area with lower, then at the end you have a net movement. If you place was heißt Duft? Duft. You smell it. So, huh? Again? Fragrance. Yeah, yeah, exactly. Some fragrance. If you place it somewhere in a room without a vent, you smell it somewhere else because of the diffusion. So you have no external force on it. This is called diffusion. The driving mechanism behind the diffusion is the concentration difference in the room in 3 dimensions. But why does it happen? Take a look there. So what is the reason that these particles move there? Because here we have also particles. They move here. What is the engine behind this diffusion? So this is just a fact. This is a fact. But this movement, this net movement, is the result. The question is, why? Assume that the interaction between them does not play a role. Just assume. It has a role, but not the dominating one. Uh, try on. Keep on trying. A lower energy level if it is yeah I know what you are thinking about. That's the engine behind, and but there is more basic, more grabbable reason behind. Assume the pressure doesn't play a role. Assume that. Just take a look on these particles in the vicinity of this interface. What do they do? They move all. They move all in all directions. Now we make a cut. The movement in this direction is more probable because there are more particles compared to the number of particles at the other side. So statistically, this movement results in more net movement to the right than compared to the statistical net movement from these particles to this direction. I have indicated this higher probability with the blue arrows and the lower probability with the orange arrows. This means the diffusion is just a statistical result. That's all. So we have a temperature, we have a random movement. That's here. Random movement. If you make a cut, then the resulting arrows in this direction, if you have more particles, is higher than if you have less particles. That's all. So diffusion is explained. And somebody has found out that this process can be stated using a law. It's called the Fick's first law. And it says that the flow rate is proportional to the gradient of the particle density. So if you have a change n2 to n1, then you have from here to there a certain gradient. And this gradient results in a flow rate. If you have an abrupt gradient, then at this moment in time, the flow rate is infinite. This in turn means you can't have an abrupt change if you have here the concentration and if you have here the x-axis. You can't have an abrupt change in concentration because an infinite flow rate would result that it is blurred out in a very short time. An infinite, what is this? We have here a, oh no, okay, this was my, I thought it was an error in a blue um, artifact, but it was just my own line here. Okay, so you can't have an abrupt change in the concentration because of the flow rate, its dependence on the gradient. Okay, but flow rate and gradient needs a combining constant, or in this time, it's not a constant, but it is a coefficient. It's called diffusion coefficient D. So the flow rate is proportional to the gradient, and the constant links this together. And this diffusion constant itself is very interesting. It is a function of the mobility. Yes, sure. You have a certain mobility of the particles, and if you have a higher mobility, then you have a higher diffusion rate. Sure, this is understandable. But it has more constants inside. It has the Boltzmann constant, which gives, together with the temperature, here the result is energy. And if you divide energy with the charge, the elementary charge, you get a voltage. So this means the diffusion constant is proportional to temperature. It's proportional to the temperature voltage. This voltage is not measurable. You cannot place on voltage meter to measure this voltage. It is an equivalent to the energy a particle has at a certain temperature. That's just a way of expression. So the thermal voltage is calculated by this value, and the thermal voltage. Now let's go to our table, to our spreadsheet. 1 second. Let's go to the spreadsheet. Where is it? It's here. It's on the way. It's coming. It's opening. 2 years later, it's opening. Here we are. As you can imagine, I have this equation also in this spreadsheet. This equation, its result is given here, and it calculates the temperature, the thermal voltage dependent on the temperature. So the temperature is given here. So if I, one second, I zoomed out once. Now I have to increase the spreadsheet. So let's put it to 400 Kelvin. then the temperature voltage is a 34.5 millivolt. And the elevated room temperature, the 300 Kelvin, gives us the 25.9 millivolt. So if we talk about the thermal voltage, we talk about roughly 25.9 millivolt at 9 again at 300 Kelvin. Okay, now let's go back to this and to here. Okay, so if we talk about the thermal voltage, we talk about 25.9 millivolt at 300 Kelvin. Well, now we have all what we need to know about flow rate. Yes, sure. Hmm. You're right. Um, if the reason for the increased number of particles is the increased doping, like you said, then for this region, you type in the mobility 2, and for this region, you type in the mobility 1, and then you have the resulting diffusion. So it's no more adjust this equation for all x values. You have here a change of the mobility. But this slide should give you one mobility for all. And this slide assumes somebody somehow placed here more dots. So we distinguish the problems into basic stuff like this. Okay? Exactly, exactly. For this topic to be explained, I have assumed that the mobility is constant. But you are very highly on the line of combining information from previous slides. That's very, very helpful. Great, great question, Mr. Rauscher. You can think about to place more particles, for instance, by injection. How you inject particles? You cannot throw electrons into the semiconductor, but somebody can do this. The photons can do this. If you enlighten a certain area with the appropriate light, with the appropriate photon energy, you absorb the photon and generate electron hole pairs. And these particles increase the number of the concentration. Or we think about this concentration difference in a diet, but later. So this is the starting point how a PN junction diet will work. Okay? Okay. So take also a look onto this YouTube video. As always, just follow these links. Now, we want to combine, no, not combine. We want to extend this stuff to the current because we don't want to just look at the flow rate. We want to look at the current without rate. density. So here we have a flow rate, just expressed with the fixed first law. And if we multiply it with the charge, we get the diffusion current density. Because what is flowing from here to there? Electrons, for instance. And if electrons flow, you have a current. So the origin of a current don't need to be the electric field. It can be just the concentration difference on different locations. Therefore, the solar cells does work. Solar cells does generate a concentration difference. And this concentration difference does generate a current if you close the loop. And that's your photovoltaic, for instance. Okay, so we have had the negative sign here, and this negative sign is disappearing here because the charge itself is also negative. And this negative sign is kept here because the charge for the holes is a positive charge. Okay, so we have two charge components, two current components. Now we have all components we need just uh, for optical Wiederholung, for repeating it optically. We have learned that the diffusion is a function of the electric field. Okay, so we have the diffusion drift current depending on the mobility. We assume the mobility is constant. We have two parts for this current, and we have also two components from the diffusion. And the sum is the convection. Diffusion plus drift is the convection. So our convection current in one direction is the drift of electron, diffusion of electron. So we have the drift, the engine is the electric field. We have the diffusion, the engine is the gradient. And the same holds true for the electric field for the holes and the gradient in the concentration also for the holes. So if we have these four components, we have the all defining equation for the current in a semiconductor, except for magnetic field. Just analyze it again. Here we have the mobility. If you pull, the electrons move. Sure, that's your applied voltage. If you have some light source in the semiconductor, you don't have also only the voltage, but you have also the tendency for diffusion. And this is true for both types of carriers. But one thing is different. The current portion caused by the voltage is unidirectional, because if the electrons move this way, the holes move this way, the current sums up into one direction. It is increasing. So one electric field, and if you have here electrons and here holes, then you have, in addition, more current. The diffusion, yeah, if you have more electrons here than there, and if you have more holes here than there, then they are counteracting. Because if the holes move here and the electrons move there, you have no current. They are neutral. That's the thinking behind. So this gradient has nothing to do itself with the current. Just together with the sign or this sign, you have the current. So which particle is moving? So here the engine defines the counter directions, but the gradient doesn't define anything. If the gradient is this way, the particles move this way. That's all. Okay, so we have now the convection current density in this equation. We take it with us to the next slides. Here we have a very complicated slide. So take a breath, deep breath, take a coffee. Hey, great. Fernando, what is the picture on your cup? I haven't seen it. Hey, wow. Beautiful. Thank you. And this one is made out of, earth. How you call it? Auf Deutsch, Ton. In English, yeah, you know. Huh? Yeah. So here we are again in the carrier motion, and now we take the generation and recombination into account. Before we continue, we sum up what are the boundary conditions of this slide. We say that the charge carrier concentrations are in thermodynamic equilibrium invariant in time. So what does this sentence mean? If we wait a long time, so all mechanisms which cause a change in the concentration has made its effect on the concentration. The result is, as a function of the time, the concentration doesn't change anymore. This is the index called a zero. Zero means we have reached the equilibrium, the thermodynamic equilibrium. So it is disturbed by injection of corresponding types of charge carriers. Now we take into account that this equilibrium value is changed, disturbed externally somehow. For instance, by light, but need not to be, just an hypothetic change. So we just change it. And then this injection causes an excess concentration of electrons and holes. What does it mean, an excess concentration? It means you have additional charge carriers there, which is above the equilibrium level. And this change, this additional value in concentration, is the excess concentration. It's called the delta concentration. So please track these deltas. If you have a delta, you have disturbed the equilibrium you have had before. Okay, and now it is very important to take this last condition into account. The injection is weak. What does it mean? We have majority carriers, we have minority carriers. We know the effect, the mass, how is the English word for the mass equation? Massenwirkungsgesetz. Mr. Botta, yes, you have helped me. Please help me again. Yeah, mass impact law. Ah, thank you. So the mass impact law defines the relation between the majorities. The majorities are caused by doping, and the minority carrier concentration is the result of the doping. Okay, so the injection, so the excess concentration is much smaller than the majority carrier concentration. Okay, now we have all conditions which apply for the following statements. What are these statements? The disturbance of the thermodynamic equilibrium due to weak injection of majority carriers and minority carriers need to be treated differently. Usually you say, if I have 1 million particles and I put 10,000 in it, then I have 1 billion particles. I don't care about this. 10,000. Here we are. This is the majority carrier concentration. If we have a lot of them, then the disturbed value, you see, the disturbed value without the zero is about the same. But for the minority carriers, it's not. Why? Because they are minorities, because there are less of them. So the injection does disturb the concentration of the minority carriers. That means if you have the equilibrium value, you see in the p-type semiconductor, the minorities are the electrons. So if I pronounce this part of equation is the minority carrier concentration of electrons in thermodynamic equilibrium in the p zone, in addition to the excess concentration. Somebody has put them into this region somehow. Again, the minority concentration of holes in the thermodynamic equilibrium in the n-type semiconductor plus the excess concentration you put into this area is the resulting concentration, the disturbed concentration. Okay, so we are just practicing the variable names and what they mean. This is the purpose of this slide. Names and meaning. The results will follow. Okay. Now we have the minority carrier concentration, the majorities. Majorities we learned, they are not disturbed. Why? Because our injection is weak. The minorities are disturbed and the excess concentration is on top of the equilibrium concentration. That's it. Now we make an experiment. And this experiment gives us this result. Please read it first yourself. Just this sentence. What does this sentence mean? This means following. Assume a grid. Assume a grid. This grid has holes. So take a look three-dimensionally. So here we have a grid. And then you have some membrane under the grid. And here you have balls. They are bouncing. Okay? Because the membrane is vibrating. What has happened? If the membrane vibrates, the balls bounce. Some of them is sitting here, and some of them are falling back, and some of them are bounced back up. What does that mean? We make a snapshot, and the snapshot says we have two balls above the grid, and the rest is on the membrane. You increase the heat, the movement, you increase the number of balls there. But that's not the topic. So this concentration is N0. So this is the equilibrium condition. Now, if you put from a bucket additional balls onto the grid, you pour it on top of this grid, you have, as a result, more on the grid, but at the same time, more which fall down, which recombine. You generate, you recombine. So if you generate additionally some number of balls, particles per second, then the concentration on the grid is increased, but at the same time, the recombination rate is also increased because of this delta number of particles. I think I have to repeat this again. So, where we start? We start with a grid where there are two particles. Why? Because we have an equilibrium condition. Some vibrate up, they keep there, and some fall down. And in the meantime, you look on it and you count, in the meantime, two particles. Now, a second person is coming with a bucket of particles and pouring it on. That's generation. You put into this area more particles. This new additional generation does not result one by one increase in these numbers. No, it does not. It also increases the recombination because if you have more particles here, you have more probability to fall down. And this increased probability means you increase recombination rate. So increased additional generation results in additional recombination. And at the same time, you have an increase in the excess concentration. That's the sentence. It's easy, but it is not a common sense in daily life. So therefore, to put this into one sentence, it is very dry to digest. Okay. So taking this statement into account, we have the following condition. If we have additional generation, the bucket and you pour it on, At a certain time, we have a stationary equation. So we have a stationary situation. At the time zero, we have, due to this additional generation rate, we have additional number of particles on the grid. But the total number, the resulting total number is not changing. Why? Because somebody is pouring all the time some number of particles on top. There are some falling down, there are some on the top, but the concentration doesn't change. Okay. Now, you stop the generation. You don't pour additional particles on top of the grid. What happens? If there are more than the two, because you have changed it, you have more than you would have by natural vibrations in this mechanical analogon. So these three, which does generate the additional recombination rate, makes the reduction the reduction of this concentration as a function of the time. Because nobody is pouring these particles on top anymore. Due to this increased recombination rate, the concentration is reducing if you stop pouring. What happens at the end? What happens at the end? Time goes to infinity. We go to the thermodynamic equilibrium. So the disturbed value reaches the thermodynamic value. And the delta n is 0, and the change rate is 0. What does that mean? It means we have here a certain concentration as a function of the time. This concentration goes down because you don't have any additional generation, and it goes down, so the change is negative, and goes down to a value which corresponds to the thermodynamic value. And this delta diminishes to 0. Okay? So this is the content of this slide. It's very heavy, it's very dry. Therefore, I have it also here in a more useful environment. Oh, there is missing one line. Before we talk about the content, please insert this line. It should go from here to there. And now this line should be also dashed. Oops. No, wrong lecture. Should be dashed. So that was originally a line this way. And the delta is between n0 in the p zone to the n in the p zone as a function of the time. Somehow these things disappeared. And this intersection point is tau e. Okay, so what we see here, If we switch off the generation, we have, due to this generation, an excess concentration. And the linkage between generation and concentration is a time constant. Again, due to additional generation, we have a higher concentration. And the value itself between the generation rate, your pouring rate, and the number of additional particles on the grid is this time constant. And the time constant is the slope of this exponential curve at this time is zero. At this time, zero. So, yes. Oh, yeah, sure. Who has kicked him off? I'm not guilty. Who has done this? He does it himself. Oh, okay. One moment. Oh, there are additional two people from Turkey. Hello, Mrs. Akbal. Hey, so sorry that I haven't seen the waiting list. It was behind the pictures. So Zoom is excellent, except the placement of the windows. The participant lists were behind the grid view of your video pictures. So I have to displace your videos to see the waiting list. And in the waiting list, it was also Istanbul. And yeah, hello. I apologize. I haven't seen you, but you were late. Hello. Selam. Oh, oh, okay. I apologize. I haven't seen also the waiting list. Okay. I'm happy that you are here, but also I'm recording this lecture so that you can take a look on the results also on the recording. So we have had this excess concentration. This excess concentration was a function of the generation rate, and the time constant was the intersection point of the slope of the tangent with the equilibrium concentration if we don't have any disturbance. So this time constant is called relaxation time or minority charge carrier lifetime. That means if we have on this grid the number of particles, the additional number of particles, how long do they keep there? If they can live a long time, then the relaxation takes time very much longer. And if the probability that they slip down, so they recombine very fast, then it is more steep. So we have something like this. So this tangent just talks about this relaxation time, like the discharge rate of an uh, capacitor at a resistor. So if you place at a voltage source a capacitor, it's charged to Q0. Then if you put this capacitor to a resistor with the Q0 at T0, and if you plot the voltage as a function of time, then you see just this figure. And this time constant is R times C. So this means if you have more generation, you have more disturbance. Correspondingly, you have more charge. If you have more charge, um, yeah, you have a longer time constant. And depending on the resistor puts back the charge, you know? The resistor puts back, so it recombines. And this path of putting this excess concentration back to the ground level is this time constant, the analogon of the RC time constant. Okay, so at this point, what I have told you up to now is here as an equation. Take it as it is. We will never use it actively in the lecture. We use this behavior in the lecture. So therefore, I want you to understand this behavior, and the equations just support this behavior. I want you to understand. That's it. Okay, so we have more vocabularies here, like relaxation time, or it's also called minority charge carrier lifetime. Now, I give you a question which helps you to make a linkage between former slides. Mr. Rauscher, I think this is something for you. If you don't know, never mind at all. Don't feel pressured. I think it is answerable by you. Let's put the question. I have a silicon. We are now in the no, we are, moment, I take this one, we are in the EK diagram. The valence band is at 0, the maximum. And for silicon, the minimum, it's somewhere here. Okay? So it's here. So you need a phonon and a trap to recombine. Now you have an additional semiconductor, which is direct. Let's say gallium arsenide, gallium nitride. Okay? Just from this picture, which one has a shorter lifetime for the electrons? Silicon? 1 second. Gallium arsenide or silicon? Just from this point of view, nothing in addition. Gallium arsenide has a shorter or longer? Shorter. You're right. Why? Gallium arsenide, 1 second. Gallium arsenide doesn't need an additional particle, no additional phonons, doesn't need a trap to recombine. It makes itself. That means if you make a solar cell using gallium arsenide, then you have to be very fast to put these electron hole pairs aside. Because if you don't do it, the phonon comes in, you generate electron hole, and then it recombines again. And that's it. So generation, recombination, except you generate and pull it away. So this time, this way of thinking using the minority charge carrier concentration is very important for understanding semiconductor behavior. But we don't have to go as deep as now. just was an occasion for me to drop a question. That's all. So the excess charge carriers are reduced. The excess charge carriers are reduced to zero by recombination after switching off the disturbance. So after zero, the generation is zero, additional generation rate in the volume of the crystal. And the time constants define the slope of this reduction. The resulting concentration is the one you have had if you wait infinite long. It is the bulk minority carrier concentration defined by which law? Mass Mass impact law. Okay, so here we are at the mass impact law. Okay, so that's the content of this slide. I have made up to now 1 hour and 5 minutes a monologue. I think it's time to make a short bio break. Let's say 15 minutes. Is it okay? Is it enough for you? No, one moment. Uh, Yesterday I have a lecture 2 blocks after the one after the next. Um, our next session we will have today, not in 15 minutes. As always, I make the same error. The next session will start at 2 o'clock. Okay? So sorry for the for making a disturbance. The next session will start at 2 o'clock. I will also record it and upload it. And if I'm lazy, I will also upload it to YouTube. Okay, see you later. Bye bye.